recording of the webinar right away. And so the webinar is recorded from here on. So if you lose your internet connection or need to step away from your keyboard, don't worry, we will send the recording out once the webinar is finished. Okay, so I'm Benoit Hamelin, I'm CTO at Arcadia, and I'm standing in for Justin Sides today. Basically, the point and the goal of this webinar is to discuss process chains and how we can use them in order to detect malware so that we can respond to data breaches in good time. So let's start with a short introduction to what I mean by process chains. So it's no secret to most users of modern computer systems. Oh, but I'm getting ahead of myself. Maybe just a little plan for the meeting today. So my intent is basically to be chattering away like this for about 20 minutes, and then to have a 10-minute and more time allocated for questions and answers. I will also be available for half an hour past the beginning of the webinar. This means I will be available up until 2 p.m. EDT. And therefore, just a bit of chatter on my end, just a bit of courses, and then you drive the show by asking the questions. All right? Okay, so I was talking about process chains, and I was saying that basically it's no secret to anybody familiar with the usage of computers or servers that programs are started by other programs, right? In a more technical parlance, processes are started by other processes, right? And this who starts whom relationship is basically denoted in terms of parent-child relationships, right? So there is an ancestry relationship between processes, and walking on these ancestry links, we can identify process chains, basically built by a process related to all its parent processes down to the initial user mode process started by the kernel when the machine boots. All right? So what is it with process chains that can help us fight malware? So when you run a computer, all right, so you're using a workstation of your own, or you're running a server that deploys a certain application or set of applications, the programs are generally started in rather regular patterns, right? So if you take a look at process chains on a certain machine, you can identify common process chains. So what happens when this machine is infiltrated? Malware will try to leverage the spawning of or forking of new processes. Why would it do that? Well, often your user mode processes will be running into certain sandboxes. So by exiting to another process, malware can exit the sandbox. It will also do that in order to elevate its own privileges by pushing a computation onto a privileged process. It can also use that in order to bootstrap code injection, or just to run its malware activity away from the site of intrusion. All right? So these various activities that malware does involves process chains that do not follow the typical patterns on the host, right? So it generates what we could consider anomalous process chains. So this begets a detection heuristic stated by whenever we detect anomalous process chains, we should be investigating the machine. All right. So in order to make sense of this principle, let us look at two cases of anomalous process chains that I have set up on this demo account on Snowboard. So the first case concerns a Windows machine, right, where a malware presents a process chain pattern. Oh, no, I'm sorry. Whereby we can uh, we can see that malware has typical process chain patterns all its own, right? And that is quite distinct from legitimate process chain patterns. So here, let me open the investigation. And now that I think about it, I have it open here in a full screen tab. So when we think about malware and the way it can, the way that it can show itself in terms of process chains, what do we think about? Well, one of the very typical process chain patterns that malware does is the so-called drop execute pattern, by which a certain piece of malware will intrude through, say, a browser or a PDF reader, and the shellcode will contact a C2 server, get a binary, and write this binary to file just to execute it right away. So this is the drop execute pattern. Another thing that it can do is to infiltrate a common program, then just spawn out of it by injecting a certain piece of code, or by spawning an interpreted program through a shell of some sort, right? So very typical examples are once again the web browser, Acrobat Reader, Macromedia Flash, or the dreaded Microsoft Office macros. So, in principle, generally, these guys, these very common workstation programs, they are not supposed to be spawning shells. They're not supposed to shell out. Okay, so let's take a look at this investigation here. So a single lead has been generated for this investigation for this Windows machine that I control, basically. So what happens on it? Well, the summary is that, in a sense, winword.exe has a child process 3 generations over of wscript.exe. wscript.exe, as you may recall, is a JavaScript interpreter that lives in the Windows System 32 directory. Okay, so let us go over the details. In a sense, the root program of this process chains is Microsoft Word, the winword.exe executable. WinWord has a parent, but we don't really care about it. We care more about its children processes. So its first step child is something called app data roaming Microsoft Word msword.exe. So this is something that spells out like a Microsoft Word executable, but that has been deployed in the user foobar's app data roaming directory. That does not look good at all, right? If we dig further, this msword.exe program has itself spawned a child process, and that child process is the wscript.exe Windows script host binary. And we even see from the command line that it's running a JavaScript process also deployed into the app data roaming directory of the foobar user. And this is where things get really bizarre. It does that from the xeyqyn directory, and the name of the script is fur FUARH.JavaScript. So I don't know about you guys, but um, I know a few foreign languages, and I'm pretty damn sure that Xican is not anything foreign at all. If anything, it's probably the result of generating a random directory name. Same thing with the FURH JavaScript word, right? So very likely this JavaScript file has been written there in a randomly generated directory in the app data roaming directory of user foobar. Now, random directories and file names are common in the temporary directory on Windows, but not quite that common on CUser's foobar app data, especially if it's been started by this weird msword.exe binary that's also been deployed into CUser's foobar app data. So to me, this smells really, really bad. Okay, so how do I go about investigating this? Well, if we are running a JavaScript file and where Microsoft Word is not supposed to be running a JavaScript file, it should be interesting to just go grab this JavaScript file and see what's in it, right? So the first thing that we should do is open the commands. Actually, we don't do it that way. Rather, we select this path and indicate that we want to get this file in this host. This takes a short while because this machine is not in constant contact with my interface. It beacons only at randomized regular intervals. So this would take a little time if I were to send the command, but as in all great cooking shows, I already have done it beforehand. And what I got from it is I actually got the file in a previous execution of this piece of malware, and I got it from there. I'm then able to download this JavaScript file and try to reverse engineer its purpose. I could also do the same. So if we go back to analyzing the lead, we saw that there were two levels of weird processes going on here. So the first one spawned by winword.exe was another one called msword.exe. So this guy, I would also want to download it. In addition, if there is a smell, a strong smell, as it happens here, of malware being deployed on this machine, I would get a full snapshot of everything that happens on this machine. How do I do that? I go to commands and I use the update info command. I just type in the investigation and host ID here, right? So the investigation is 677, the host ID is this, and bam, apply. And the result is, as we saw here, oh, bad investigation. As we saw here, a bunch of fresh information about what's going on this machine. So I get a full snapshot of all processes running on the machine, refreshed host information, list of services, list of drivers, and what kind of tickles me right now, a list of auto runs. If I go and take a look at these guys, so I see here, okay, something about VMware, something about PowerISO, user init, that smells good, stuff in winlog on shell, isolated commands, yada, 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 very common stuff, very common stuff. Alternate shell, this is probably something legit. I'm not a big Windows expert here, but what I can tell you is that every other autorun key on this machine is about stuff deployed on C Windows something something, except this one here, which is also deployed into the app data subdirectory for user foobar. So this again smells bad, especially given that it's something that calls itself SVC host update. I'm pretty sure that Microsoft, whenever it updates its SVC hosts, will not go through the app data local of some user. So I would likely grab this as well and reverse engineer it and find that this is actually a stage 0 component for the Turla malware. All right. So in order to analyze these autorun dumps more quickly, we're also working on a way of computing a diff of autorun snapshots between a previous version, presumably would have happened before the malware deployed itself, and this version, and this diff would likely show me this one entry added, and would also tell me an idea of the time frame at which when this new autorun has been added. Okay, and that completes my investigation of the first case. So we saw that not certain, but malware in general, especially on Windows, have very common process chains of their own. And so singling out those process chains help in detecting the threat. The second case I wanted to go over, and I see that I will overspend my time, so please feel free to tell me to shut up if you really want to ask questions right now. So this second case is about the fact that often, especially on Unix and Linux systems, malware forks a new process in order to elevate its privileges. So here we're confronted with a much simpler example, okay? On Unix, there is such a thing that we called setuid programs. So what do they eat in winter? So typically when you run a program on Unix or on Linux, this program runs with the privileges of the user that starts it, right? So if I run an editor program, this program runs as Benoit Hamelin with my limited privileges. But setuid program accepted this rule. Instead of starting with the privileges of the invoker of the program, they start with the privileges of the owner of the program file. And since most program files are owned by root on any given Unix system, setuid programs owned by root will effectively start with root privileges, even though they are not started by the root user. So this means that when these programs start, they provide a free privilege elevation to the user that starts it. Okay, so in general, it is very well known that setuid programs are a huge security hole. Okay, because many of these programs are more complex than the analysts or programmers will bother to remark. And from this complexity, they can be exploited to run arbitrary computations with root privileges. All right? So in order to make sense of what happens with this setuid program, let's take a look at this investigation now. So what I see here, let's close those keys. We see that I have a parent process, a simple bash script that I was running on there. And what did I do there? I just typed the name of a setuid program. Okay, now project yourself as a hunter who's just got an alert of this type to investigate. Okay, so it's not me, it's somebody that sees, okay, this user there called Hamelin has been running this program here, and this program has user ID 0 whereas its parent has user ID 1000, right? If we take a look at usernames, 1000 means that this user Hamelin was doing something, and all of a sudden, his computation runs as root. Okay, so there's two possibilities here. First possibility is that this guy is running a privilege elevation exploit. So I would want to check out the content of this test privilegiation program. The other possibility is that he's running a setuid program. So the first thing I will do here is simply go check the rights with which this file has been done. And for that, I sent a simple ls-la command. Okay, and we see from here that yes, this file belongs to root, and yes, from this little s here by the RW, we see that it's a setuid program. So this is a program that could be used against the owner of the work. In this case, it's a workstation, but against the owner of the machine in order to elevate privileges if it can be exploited. Okay, so two things I want to do here. First is I get a copy of this file to go and audit in order to, if I can find an exploit for it myself. If that's so, I will sound the alarm to IT. They have to take it out right away. And in any case, I will go and warn IT of this security hole and suggest a better approach for providing elevated privileges when running this program just to certain users or under certain circumstances by using things like the pseudo program or something else like this. And that also concludes the study of this second case. So in conclusion, before I start taking questions, I wanted to point out again that the typical usage of computers will result in common process chain patterns. Your malware will tend to generate off-pattern process chains, and we must look for these. What do these things look like? They will look like atypical parent processes, like in our MS Word example. They will look like, for instance, signed processes that spawned unsigned programs. We did not see an example about this thing. Another thing we can see is child processes having higher privileges than their parent processes. This is also something that should raise your attention. You should investigate as soon as you can. So right now we're also working on an artificial intelligence engine to identify the most common process chains on all machines that we monitor and eventually be able to detect anomalous process chains more generally than we do already. All right, thank you. And on this, I will start taking your questions. Please, not everybody at the same time. I will not name your name. Okay, here, I got one question. So I'm asked about the set GID bit that we can set in addition to the set UID bit. Okay, so this mechanism, I will explain it again. This mechanism is made in order to accept the rule that when you run a program, it should run with your user privileges and the privileges of your main group. So when you set the setuid or setgid bit in the rights of an executable file on Unix in general, this makes it so that when the program starts, it will start with the user privileges of the owner of the file if the setuid bit is set. And in the case of the setgid bit, it will start with the group privileges of the group to which this program primarily belongs. Okay, so this is typically less of an issue uh, because the primary privileges that a program assert stem from the privileges of its associated user, not the privileges of its associated group. That said, the privileges of the associated group to a program can enable it to go and reach out to files that normally it would not have a right to check. So there is certainly a problem there as well. So the setuid, setgid bits, uh, you they should be whenever they are used, they should be reported to the IT department of the organization on which you detect their usage, and they should be advised to use something else, because likely whenever these programs are generated, they will raise an investigation, and even though this usage of those programs is typically legitimate, it will generate noise, which prevents the hunter from drilling down to the proper malware. Any other question? Okay, so I'm getting another question here. So I'm being asked, besides, so we've seen an example where Word macro would spawn some file called msword.exe, and that in turn would spawn a W script, JavaScript execution. So I'm being asked here what else we look for in terms of illegitimate processes that can be spawned by the common workstation programs, such as Office programs or web browsers or what have you. So the other things that we look for typically are batch files. So .bat programs, this, or more in general, we look for the execution of cmd.exe. A Word program should have no reason to spawn out a command shell. Another thing that we actively look for is PowerShell programs. These are awesome to be encoding various types of malware, especially very powerful stage zeros, and therefore they we look for PowerShell every single time it pops up, whether it's as a child of Word, which makes the smell even stronger, or as a child of Explorer or anything. Other things we look for are rundll32.exe, which allows one to run to spawn a program off of a DLL, as well as cscript.exe. So these are and in addition to wscript.exe, which we've seen in my example, these are the 5 things that we are very much worried about whenever they spawn off as child process, I mean, to some Office or workstation program. All right, if you allow me, I will wrap up the official presentation of the webinar. I will stay online up until 2 p.m. So if you want to ask me some questions in private, discuss with me, whatever, please just send me private messages instead of public chatter. And you can also send me emails. I will input my email address here on the chat window. Feel free to send me emails over there with your questions, and I will do my best to answer it promptly. Thank you very much for your attention today, and I tell you all bye-bye. See you next month.